Great. Thank you. Thank you very much. I'm terribly sorry I cannot actually be in Bangalore in person. I had a wonderful time when I visited ICTS in November. Unfortunately, I had to be elsewhere during this period, but I'm very happy to be able to talk to you guys. Yeah, as was announced, I'm going to talk about some new directions in searching for the dark universe. And, here's the basic bottom line. You've probably seen this sort of slide before. We definitely know that there is a particle out there called the dark matter. And the observations of the bullet cluster tell you that this new particle, that whatever the dark matter actually is actually a new particle, as opposed to it being a modification of the law of gravity. Further, given that it's a new particle, it's very reasonable that this particle has non-gravitational interactions. So far, we've only observed the dark matter through gravity. It's very reasonable that it has some non-gravitational interactions to the standard model. If it had those non-gravitational interactions, it's very important to detect them, because by doing so, not only do we learn something about the identity of dark matter, why the dark matter exists, what is actually producing it, things of that kind, but also it gives us access to some new sector in particle physics. And hopefully we can use that new sector to learn more about the laws of nature. So given that there is a high interest in trying to find these other non-gravitational interactions, the key question one has to ask is basically technologically, how do we do it? What kinds of techniques do we need to detect the dark matter? And this is going to be hard precisely because the reason why we call the dark matter dark is because it doesn't interact much with the standard model. It doesn't interact much with our particles. So these effects of the dark matter are going to be pretty weak. So we need techniques with very high precision in order to be able to see these very weak effects. And that's kind of where the story gets very interesting, because in the last 2 decades or so, there have been some very impressive developments in the field of precision instrumentation. So today, for example, one can measure magnetic fields as small as 10 to the minus 16 Tesla, or even smaller, with squid and atomic magnetometers. And also, one can also measure accelerations as small as 10 to the minus 13 times the acceleration due to gravity, and that is through atom and optical interferometers. So these are technologies that actually exist in the lab. This is not some pie in the sky quantum sensing. This is just technology that you can actually go and make in your laboratory. And so it's interesting to ask, how could one use these kinds of technologies to detect things like the dark matter? By the way, what's also exciting is the fact that in both of these fields, and I've kind of been involved in thinking about these things now for about a decade or so, and I would say that every few years, these numbers get better, because the experimentalists who develop these kinds of technologies, they see ways in which these numbers can be improved. And nobody has really thinking that you've approached a point of saturation. These numbers regularly shift every few years or so. So it's actually interesting to think about how you can use not just current technology, but also like reasonable extrapolations of current technology to kind of see how that can be used to detect new physics, in particular the physics of dark matter. So what I'm going to do in this talk, as sort of a very brief overview, is to start with a little bit of theory, just to give you guys some idea of what kinds of dark matter particles may be of interest. And then I just want to talk about 3 experiments. One to detect a particle called the axion with the nuclear magnetic resonance, another to detect a particle called the dark photon with a fancy radio, and the last would be to detect dark matter with fancy accelerometers, like the ones that LIGO, for example, is using. So if you want to understand what kinds of dark matter might be interesting, right, we should first understand how little we actually know about dark matter. So if you ask a particle theorist, what could the dark matter be? Well, we know the dark matter is a particle. So naively, for a particle physicist, a dark matter is any particle whose mass, let's say, could be above 10 to the minus 43 GeV. And one might want to cut it off at the Planck scale to have 10 to the 19 GeV, because above that, well, the dark matter could really be above that. It would not be a fundamental particle, it would just be some kind of composite object. But in this vast landscape, we can do slightly better. We know that the dark matter actually fits in the galaxy. And the fact that the dark matter fits in the galaxy puts 2 non-trivial limits on its mass. First, if the dark matter mass gets very, very light, and this is just generally true, as the dark matter mass gets very, very light, since we know the total amount of energy density that is there in the dark matter, as the dark matter mass gets light, its number density has to increase. Now, for a fermion, you actually know that there is a limit to how high the number density can go. because you can only put, one fermion in a given mode. If you have two spins, of course, you can put two of them. But there's a limit on the maximum number density that a fermion could actually have in the galaxy. And given that the dark matter actually we know exists in things like dwarf galaxies, it turns out that if the dark matter mass is below something like 10 to 100 electron volts, the number density that you need would be so high that Fermi degeneracy will prevent you from filling up your galaxy with the required amount of dark matter. So if the dark matter is a fermion, its mass has to be above 10 to 100 electron volts. If it's below, if it's a boson, this limit doesn't apply because you can keep packing in as many bosons as you want into your mode. But even for a boson, ultimately, as the mass of the boson gets very, very small, its de Broglie wavelength will get very, very big. And eventually, the de Broglie wavelength gets larger than the size of, say, a dwarf galaxy. You know that the dark matter wavelength will not fit inside the galaxy, inside these galaxies. And that puts another non-trivial limit of around 10 to the minus 22 electron volts on the lowest mass the dark matter could have if it's a boson. Anything above this is basically just a guess, right? This is all we observationally know about the mass of the dark matter. And so one popular guess is that the dark matter itself may be tied to the standard model scale of around 100 GeV. And that's, of course, theoretically possible. And that gives rise to the paradigm of the WIMP, the weakly interacting massive particles. And indeed, there are many theoretical reasons that you've probably heard of why WIMP dark matter is interesting. And indeed, one should go look for them. But we have been looking for WIMP dark matter for a long time and we haven't found it. So I think there is good reason to also look elsewhere in this large parameter space. So the kinds of dark matter particles that I will talk about today are particles like axions and massive vector bosons. And, I'll broadly be interested in these particles in a mass range from about 10 to the minus 22 electron volts to about 10 to the minus 6 electron volts. Obviously, one can convert mass to frequency. The 10 to the minus 6 electron volts corresponds to about particles whose mass is about a gigahertz or so, and going all the way to an inverse year at very, very low frequencies. And this range includes popular dark matter candidates such as the QCD axion, things of this kind. Okay, so when the dark matter is this light, it's more useful to think of the dark matter not as individual particles, but rather as waves. Obviously, as particle physicists, we know there's no fundamental difference between a particle and a wave. They're just equivalent to each other. But the reason why it's more useful to think about this as a wave is because you have so many particles occupying a given mode of the field that it is really just behaves like a classical wave, as opposed to a particle, which would be individual particles coming and doing something. So how do we think about the dark matter wave, these bosonic dark matter waves? Well, let's think about a wave that we understand very well, which is basically the electromagnetic wave of the photon, right? So in this picture, I've shown a laser, and there's an electromagnetic wave coming out of it. One way about thinking about this laser is indeed as photons one by one, or a large number of them coming out from this laser. But a equally sensible way of thinking about this is to think about the photons as effectively being the result of an electromagnetic wave, which has an amplitude E0 and a frequency omega. And one way you would detect these kinds of photons is by trying to detect the time-varying electromagnetic field associated with the photon. So for example, more than a laser, if you think about a radio wave produced by, I don't know, Doordarshan. I come from India in the 1990s when Doordarshan was the dominant channel. There are obviously much better television channels in India today. But if you just think about how you detect radio or waves of that kind, what actually happens is that there's an electromagnetic wave that is being produced by your TV station, and you detect that electromagnetic wave because as that electromagnetic wave goes through an antenna, it will drive currents in the antenna up and down, and it is those currents that you're actually detecting, and that's how your Doordarshan actually reaches your home. So we can think about dark matter also in a very similar way, where we basically say associated with the dark matter field, there is a classical field, right? Just like how for the photon, there's a classical electromagnetic field. Similarly, for a dark matter particle also, there is a field associated with it. And that field very generically has a non-zero amplitude when the universe was created. We don't know how the universe was created, but in the very beginning of time, the field just has some non-zero amplitude. And when the field has a non-zero amplitude, there will be an energy density associated with it. Just like how for the photon, when there's a non-zero amplitude for the field, there's an energy density associated with it. Okay. The one difference between the dark matter and the photon is that the dark matter is massless. Sorry, the dark matter has a mass. And because it has a mass, its momentum and energy are not simply related like they are for the case of the photon. For the photon, of course, the frequency and the momentum are obviously equal to each other.
Hello.
Whereas for the dark matter, essentially, you could have zero velocity, which basically means the momentum.
Surjeet?
Yeah.
Can you hear me?
Yeah.
Yeah, actually your voice is little low. Here somehow cannot increase the sound. So can you somehow from your side increase the
My volume? Oh, is this better? I mean, I don't know how I'd increase my volume. Is it better now?
Okay, then sorry. Go on.
Okay. Sorry. Yeah. I don't know what I mean. I feel like my microphone, whatever. I can't really control anything about it. I think this is what it is. All right. So hopefully it's better now.
Okay.
All right. So the dark matter, of course, has just it's a non-relativistic particle, so its velocity can really just be very small or even be zero. So that's the difference between the dark matter field and the photon field, because the dark matter could literally have very small momentum. So the way we think about these particles is that in the early universe, we say, look, the universe was created at that point. The dark matter had some initial amplitude, and that amplitude has some energy density. And you can show that this amplitude redshifts exactly like that the energy density in this amplitude redshifts exactly like that of dark matter. So how does the field look like? Well, it's just some A naught cosine MT. And what that means is that you now have a time-dependent field oscillating up and down at a frequency equal to the mass of the dark matter. And in the early universe, we would just think of this dark matter field as being completely spatially homogeneous. Everywhere in the universe, it has exactly the same value. It is just going up and down in time. Of course, we don't live in the early universe. We live today. Today, the dark matter field has fallen into the galaxy. All kinds of things have happened to it. And so effectively, today, we would think that the dark matter field looks pretty random. Now, even though the dark matter field is pretty random, it still has some properties that are coherent in some sense. And one can think of those in the following way, right? The dark matter field, let's say, has one value here, and you want to know how far in space you want to go before the field value changes by order 1. In other words, you're trying to compute the 2-point function of the field. It has one value here. You ask, how far do I have to go before the field value changes by order 1? If you think about that problem in Fourier space for a second, you realize that the distance that you have to travel in order for the field value to change by order 1 is equal to the de Broglie wavelength, right? Because it is e to the I kx. It's that kx that actually allows the field value to change by order 1. And given that we know what the momentum of the dark matter is in the galaxy, we know that the minimum correlation length you must have is of order 1 over mv, where m is the mass of the dark matter and v, the velocity of around 10 to the minus 3, is the velocity that the dark matter has in the galaxy. Now, for an experiment, I'm interested in measuring the value of this field. And I'm not just interested in the correlation length, I'm interested in the coherence time, which is basically how long do I have to spend to sit at a given point in space and keep measuring the value of this field before it changes by order 1. And the point there is that you can wait till this correlation length of order 1 over mv passes through you. The relative velocity between you and the dark matter is also order v, and therefore the coherence time is 1 over mv squared. And you see, this is kind of where the story gets very interesting, because if you look at these particles like axions, things of this kind, the physics that produces these particles comes from extremely high scales. It can happen at 10 to the 15 GeV, 10 to the 12 GeV, or whatever, some very, very high scale. Yet the dark matter particle mass it produces, for example, of the axion is very light, is about, let's say, a megahertz or so. And then the coherence time for the signal is essentially 1 over mv squared. And since v is about 10 to the minus 3, the coherence time is something like a factor of 1,000,000 larger than the period. So if you had a dark matter particle like the axion whose mass was a megahertz, the coherence time is 1 second. And experimentally, this is very interesting, because if you think about it, I can build instruments in my laboratory that are able to respond to classical fields that oscillate up and down at a frequency of about a megahertz. We know how to build those things. Plus 1 second is a fairly long time for me to sit out there and acquire the signal. So this combination of facts actually makes it very interesting to go and think about experiments that can detect the effects of this oscillating dark matter field, just like how I detect a radio wave by the time-varying electromagnetic field that causes a current to go up and down in an antenna. And because I can have 10 to the 6 oscillations longer, I can try to come up with a resonant experiment where I'm able to just hone in on the dark matter signal at a specific frequency and detect that. So that is the general plot of this entire talk. What kinds of particles are interesting? So one key point in the story is that I'm thinking about extremely light particles. And when I'm thinking about extremely light particles that interact with a standard model, it's very reasonable to ask, well, why do quantum corrections not give large masses to these particles? And therefore, one would typically think about particles whose mass is this light because of some kind of symmetry. Now, the moment you utter the word symmetry, you realize there's additional mathematical structure that goes into the story, which allows you to classify the kinds of interactions that the particle could really have. And in my opinion, there are really only about 7 possible interactions the particle could really have and still be technically light. Okay, so let's kind of write down what they are. So let's think about spin zero particles. These are particles that are bosons, like axions, things of this kind. And there are only 4 possible interactions that a spin zero particle could have and still be technically light in terms of symmetries. And these are the possible interactions. It can couple to electromagnetism to the interaction A over F, F of dual. That's the usual coupling of the axion to photons, which many people look for. The second possibility is that this particle couples to gluons through a coupling A over F GG dual. If it has that coupling, that is called DQCD axion. It can also interact with the spins of standard model fermions like electrons and nucleons to the operator d mu A n bar gamma mu gamma phi n. Okay, and it can generically interact with particles like the Higgs through couplings of the form G phi Higgs squared. These are things that are, it's called the Higgs portal or the relaxion coupling. Another possibility is that the particle has spin 1, right? And again, if you want it to be technically light, then one has to write down anomaly-free interactions in the standard model, which then gives you 3 other possible couplings. So for example, I can interact through the dipole moment of nucleons through interactions like F prime, N bar, sigma mu nu N. So F prime is the field strength of the new vector gauge boson that I put in the spin 1 gauge boson. So just like how the neutron and the proton have dipole moments under the electromagnetism, perhaps the neutron, the proton, and the electron could also have dipole moments under this new dark gauge boson. One other possibility is that the particle interacts with standard model through a kinetic mixing with the regular photon. So that is an epsilon, that is the coupling, and then F prime is a new dark gauge boson, and there's a regular photon. So there's a kinetic mixing between the regular photon and the new dark gauge boson. That's a possibility. And the last possibility is that you could interact with standard model through some kind of conserved current. An example of this conserved current would be something like the B minus L gauge boson. So these are the 7 possible ways in which you can actually interact with standard model and still be naturally light. And if the dark matter is any of these things, what you would do is that you would actually take the dark matter classical field and you would stick that in these operators. And when you stick that classical field in these operators, because it's a dark matter, the field would be oscillating back and forth. And because it's oscillating back and forth, there are going to be time-dependent effects in all of these interactions. And you go and look for these time-dependent interactions. And a large number of dark matter searches for non-WIMP particles have dominantly been focused on the axion. And they've pretty much only been looking for a specific kind of axion which interacts with electromagnetism, A over F, F of dual, for a mass around a gigahertz or so. And what in this talk I will tell you about is basically the way to search for a much broader class of dark matter interactions, talking through all these possible couplings over a much broader range in frequency. And in all of these interactions, what will be important is the fact that since the dark matter is at a specific frequency, we can think about these resonant sort of interactions where you basically realize that, oh, I should only get a signal at a specific frequency. If the signal is anywhere, and if the signal is only at one frequency, then I'll know it's a dark matter. If it's something else, if it's all over the place, it's very likely noise. Now, a skeptical experimentalist may look at this and say, why do you care about naturalness? Because even though naturalness sounds like a nice theory point, it is in fact the case that observationally, the world appears to have a finely tuned cosmological constant. It also appears to have a finely tuned Higgs boson. So why should anyone care about naturalness? That's a very sensible attitude to take for an experimentalist. And let me convince you that even if you take that very skeptical attitude, the number of possible experiments you need to do is actually fairly limited. So let's take a very experimental point of view and ask, well, suppose you do have this dark matter field. What can this dark matter field observationally do to standard model particles like protons, electrons, neutrons, and photons? So really all we're asking is, if I have a classical field, how can the classical field actually interact with standard model particles? And there are really only a small number of ways in which this can experimentally happen. I have a dark matter field, so think of it as an oscillating dark matter field going up and down. What can this dark matter field do? It can go and drive currents in some kind of a circuit. It can cause some spin to rotate. It can exert a force on standard model particles, and it can change the values of fundamental constants. These are pretty much the dominant ways in which a classical field is able to affect standard model particles. Now, the key point is that if it's, say, one of the first two things, say the dark matter comes in, drives a small current will create a small magnetic field, and I can detect that magnetic field with a very precise magnetometer, like a squid or atomic magnetometer. The dark matter particle can come in and cause some spin to rotate. If I take a bunch of spins together and the dark matter particle causes those spins to rotate, then that will change the magnetization of that system. And that is, again, something you can measure with a squid magnetometer or an atomic magnetometer. And finally, the dark matter exerts a small force on materials that would cause tiny accelerations. Those are, again, things you can go and measure with an optical or atomic interferometer. And finally, the dark matter, let's say, changes fundamental constants, like the fine structure constant or the mass of the electron. Those will also show up in these optical and atomic interferometers, because essentially, if you think about an optical interferometer, you may use it to measure the distance between 2 points. But even if the 2 points are not physically moving, if, say, the fine structure constant or the electron mass changes, you are actually measuring the distance between these 2 points in units of the wavelength of the light. Now, the wavelength of the light itself is determined by the mass of the electron and the fine structure constant. So the fine structure constant, etc., actually changes. You're going to realize that actually the ruler that you're using to measure the distance between these 2 points will actually fluctuate. And therefore, even if the distance between the points is actually not changing, since your ruler is changing, that will show up in your experiment as a signature. So in all of these cases, we are once again simply going to think about the fact that the dark matter gives you an effect at a very specific frequency. So I'm therefore looking for a narrow band signal in all of these experiments spread only around the dark matter mass with a width of around 10 to the 6, 10 to the minus 6. So let me now rapidly tell you about the 3 experiments. The first one is Casper. The whole idea of Casper is to look for the effects of axions on spins. So let's say we take a neutron and say the dark matter goes through this neutron, and it interacts with us through the interaction d mu a n bar gamma mu gamma phi n. If you look at that interaction and you write that in the non-relativistic limit, you're going to see that the interaction is basically that of a velocity interacting with the spin. So that basically will cause the dark matter, the nucleon spin to wobble back and forth. And that will change the magnetization of the sample. And that is something one can go and measure. Other kinds of dark matter interactions, for example, the dark matter had the standard model particle had a, let's say, a dipole moment under the dark field, just like how a real photon causes, a real magnetic field causes spins to precess, the dark magnetic field will also cause these spins to precess, and you can go and measure that. If you had the QCD axion, and say you are coupling through the GG dual coupling, the QCD axion will induce a tiny electric dipole moment for the nucleon. And if you now apply an electric field, that will also cause these spins to precess. And therefore, you can again measure that spin precession by the change it causes in the magnetization. So the whole point of Casper is that if you're measuring these spin rotations, you can detect particles that cause spin precession. So how do we do it? We take a sample of material and align all the magnetic fields in one direction and let the dark matter do its thing. The dark matter comes in, it causes these spins to rotate. And then you can measure the changes. You can measure the change in the magnetization by using a squid pickup loop, for example. And there's a natural possibility of a resonance in this kind of story because the spins naturally want to precess at the Larmor precession frequency set by the external magnetic field that you put in the system. We, of course, have no idea where the dark matter signal actually is because we don't know the dark matter mass. So what we do in these experiments is that we simply change the value of the magnetic field. And by changing the value of the magnetic field, we can scan and potentially find one particular frequency where the dark matter signal actually exists. And that will be a way in which we detect the dark matter. So in the interest of time, I'll simply point out that Casper has made quite a lot of progress, and we are optimistic that over time, we will be able to cover a significant chunk of parameter space in these dark matter experiments. Let me then talk to you rapidly about the DM radio experiment, which is being constructed at SLAC right now and many other institutions as well. And the main idea here is that we're thinking about the dark matter that interacts with photons through this kinetic mixing coupling. And what it effectively looks like in this case is that the dark matter particle will essentially interact much like the regular photon, except regular standard model particles that have charge under the normal photon, they acquire a tiny charge under the dark photon. So how do you find this kind of stuff? Well, what you do is that you're looking for the dark matter electric field, because the dark matter is just this field oscillating up and down. There's a dark electric field going up and down. So what you can now do is that you can create a shield. The shield will block the regular standard model, and it doesn't block the dark electric field. So dark electric field can go through the shield and drive currents inside that shield. So the DM radio experiment is doing exactly that. We put a shield. The shield blocks regular standard model particles, but the dark photon will come in, and we can stick an LC resonator inside this particular shield, and the dark electric field will drive currents in this LC resonator if the resonance frequency of the LC resonator actually matches the dark matter frequency. And if it did, there would be a resonant response, and that is what we would read in our experiment. So once again, this experiment has, I think, potential to read a significant chunk of parameter space. So in the last couple of minutes, let me rapidly tell you about how one can detect dark matter with accelerometers. And the basic idea here is that dark matter particles, such as, say, the B-L interaction, under this interaction, protons, neutrons, electrons, and neutrinos are all charged. But it has the interesting feature that electrically neutral atoms will be charged under B-L. And that is because in an electrically neutral atom, you still have neutrons, and the B-L interaction charges the neutrons. So the neutrons have a non-zero charge under B-L, which basically now means that if you had this dark B-L electric field around, you will be directly exerting forces on things like atoms, and those will create accelerations. Similarly, particles like the relaxion, which we talked about earlier, which is that you have a particle phi that interacts with the Higgs interaction. And since the Higgs is ultimately responsible for giving mass to the standard model particles, this kind of interaction also causes mixing between the dark matter particle phi and, say, various standard model masses. And because these fields have a gradient in the locally, because there's a velocity associated with them, that gradient effectively exerts a force on these particles, and those forces will also exert accelerations on dark matter particles. So the way we look for these experiments is that you can go to these tests of the principle of equivalence. Basically, people look for objects falling on the in the Earth's gravitational field, and you want to see if one particle falls faster than the other. Under gravity, it won't. But if you think about the B-L or the Higgs interaction, these things don't care about gravity, and the dark matter is directly exerting a force on you through those interactions. And so typically that will cause different particles to fall differently in the gravitational field. So what one can do is, for example, take a torsion balance where I've got titanium and beryllium. They're both materials that are stuck or whatever. And the dark matter now comes in, and it can exert a differential force on titanium versus beryllium, for example, because titanium has a different amount of neutrons than, say, beryllium, which then causes a differential rotation between the two of them. And that causes its angle to twist. And that twist is something one can actually go and measure. Okay. One can also similarly look for these effects in pulsar timing arrays. So you may have heard of pulsar timing arrays. And the idea there is that you're looking for low frequency gravitational waves in pulsar timing arrays, because what's happening is that a pulsar is sending you signals at constant rates. And in a pulsar timing array, you're looking for the possibility that a gravitational wave went by, and it causes a modulation in the distance between you and the pulsar. and that is something you're able to read. But now what will actually happen is that if you actually have a dark matter particle pushing on you, the dark matter particle will also cause relative motion between the Earth, for example, and the pulsar. And that again will cause a modulation in the distance. And that is something you can go and read with these pulsar timing arrays. And if you had particles that change fundamental constants, like the mass of the electron, what will happen is that even if the pulsar is sending you pulses at a constant rate and the distance between you and the pulsar is constant, the timing that you're using to measure the time of arrival on the Earth will be messed up because electron mass is changing. As electron mass is changing, your frequency standard on the ground is changing. And that will again, therefore, show up as a modulation in the arrival time of the stuff. So once again, these experiments have the potential to cover a lot of territory that hasn't been probed before. So with that, let me actually conclude. And what I am motivated by is the fact that if you think about the story of WIMP detection, in 1985, this entire game began because Goodman and Witten sort of thought about how one could actually look for the scattering of dark matter particles with various detectors. And the last 20 to 30 years, we've actually significantly probed a large part of WIMP parameter space by orders and orders of magnitude, many orders of magnitude beyond what was initially conceived by Goodman and Witten back in the day. And now I would say there is a similar approach seems possible in searching for these oscillating fields, in that one can start with a small experiment, understand how it works, and then keep scaling it. As you keep scaling it, you will be able to probe more and more territory. And indeed, I would say that we are, I think, in an exciting time where, much like how we search for the scattering of WIMP dark matter particles, we now have the ability to search for these very, very low frequency dark matter particles, going all the way from about 1 over year frequencies to about a gigahertz or so. So with that, let me stop and take any questions if there are any.
Thank you, Surjeet, for such a nice talk. So now time for questions.
Yeah. Is there any specific reason why you use titanium and beryllium only in the case of atomic interferometer? Like you can use
for torsion balance. Yeah, so usually what you want is basically a system where the neutron to proton mass ratios are quite different. Because ultimately in all of these cases, right, that you want the maximum signal difference between one element and the other. And so it's advantageous to have a light element and a heavy element together because the neutron to proton ratio is quite different between the two. So in beryllium, for example, the neutron to proton ratio is, I think, they're basically the same, 1-to-1, whereas in heavier elements, there are more neutrons than protons, otherwise you wouldn't have nuclear stability. So that is one of the reasons why you want, I think, a light element in concert with a heavy element.
Okay, thank you.
Yeah, Surjeet, can you just comment on this coherence time? How does that affect the signals that you see, and what do you need to ensure that you measure? I mean, so after coherence time, the signal would change? Is that?
Yeah, that's right. Yeah, so right. So what happens is the following, right? That basically we can think about how the signal to noise ratio will increase. So here are the following regimes of interest, right? For a time that is short compared to the coherence time, your signal is very, very sinusoidal, which basically means that, let's say, think about it as a child on a swing, right? The usual kind of thing. So I'm standing there and I'm pushing the child back and forth. And if I'm pushing the child back and forth resonantly, the amplitude of the oscillations will grow linearly in time. So until the coherence time, the signal will kind of increase linearly. Okay. Now, in general, in all of these experiments, right, the more you integrate, the noise in the experiment will decrease as 1 over square root of t. So the signal to noise in the beginning will grow as t to the 3/2. Now, once you go past the coherence time, the signal just looks like noise because it is basically, the same as noise, right? It's incoherent. So at that point, the statistical question you're really asking is the following. You're basically saying, look, at this very specific frequency, right, there is an extra signal. So basically, you have some large noise floor. There's some large noise. and you're saying, oh, at this very specific frequency, there's a little bit of an extra signal because of an extra power that's actually coming in from something externally coming in and moving. So at that point, what you're asking for is there an extra little tiny bump at a very specific frequency band? So that becomes more like a bump hunt, at which point the signal to noise will basically scale a square root of t in the power. And that is because of the fact that you're just asking, is there extra power in some specific band compared to its neighbors?
You were talking, you mentioned about this pulsar
Yeah.
arrays.
Yeah.
You know, and a gravitational wave goes through and it distorts the signal. And then on top of that, you have so the signal gets modulated due to the gravitational wave. On top of that, because of dark matter, it gets further modulated.
No. That would be too difficult, right? So
yes, exactly. Okay.
Yeah. So, well, I said that only because that's how pulsar timing arrays work. That's what they're looking for. But basically, let's say there is no gravitational wave at all. Okay. Then what can happen is that the dark matter can still exert a force on you and the pulsar, and that would still cause relative motion. Or let's say there is no relative motion even, the pulsar is still sending you light at the same time it's supposed to be sending it to you, and the distance between you hasn't changed. But the electron mass, let's say on the Earth, has changed a little bit because of this oscillation. That will then mean that you will infer the time of arrival to have changed. So it's got nothing to do with the gravitational wave. I just said that simply because people have heard of it before. And it's a very similar effect you're looking for in many ways. But obviously the details are quite different.
But then in that case, you're not really using the whole array. I mean, you do it for each of the pulsars.
Yeah, yes and no, in the sense that pulsar timing
Then
arrays,
add it
they
up.
do gain with the number of detectors they have, right? The difference is that, for a pulsar timing array, they're looking for quadrupolar gravitational waves. So they have, they're specifically looking for one side expanding, other side contracting.
Yes. Yeah.
In this case, it depends quite a bit. So if it's a scalar, for example, the effect will be homogeneous in the sky. Whereas if it's a vector, it would be oriented in some particular way, right? So there are, I think, differences in the analysis that you do because the gravitational wave is a quadrupolar thing, and this one is not. So one requires work to do that, but I think it can be done.
And just one more quick question. Can you once again go over the logic of how you get the correlation length?
Very good.
Yeah.
So good. So there are two ways of thinking about it. So one way is that what is the correlation length? Right? We're basically saying I have one field value here, and I want to know how far do I physically have to go in space before the field value becomes very different, right? So how does the field change from one place to another? Well, in Fourier space, that corresponds to me writing down some cosine omega t minus kx, right? Because it is that kx part that actually causes the field value to change. So the distance x that you have to travel is 1 over k before kx becomes an order 1 quantity. So how big is k? Well, k is the momentum. K is essentially mv. So the distance you have to travel is 1 over mv. And then what we're saying is that if that is a correlation length, how much time do I have to sit and measure the signal? Well, I have to travel a distance 1 over mv, and I'm traveling the distance 1 over mv with a speed v. And so the coherence time is 1 over mv squared. That is one way of thinking about it. An equivalently good way of thinking about it is to say that, look, the dark matter has some mass, okay? So it just wants to oscillate up and down at that specific energy. But in the galaxy, the dark matter fell in, it acquired kinetic energy. Its kinetic energy is order 1/2 mv squared. And therefore, if I wait for a time that is longer than 1 over mv squared, then of course that 1/2 mv squared piece will spread the frequency around, will spread the phase around. So you kind of see that they both give you the same estimate, essentially.
Is now the average velocity of axions in the halo? I mean, in either of the explanations?
Yeah, the average velocity axion on the halo will be about 10 to the minus 3.
So that's the way you would use.
Yes, yes.
Yeah, just to follow up on that, isn't the energy mass of the axion plus 1/2 mv square? So Isn't the coherence time actually 1 by MA rather than 1 by MA?
No, see, the 1 by MA is constant, right? So what do you mean by coherence time is basically you are talking about what would cause it to actually change. So the MAT, that is the frequency at which the signal is actually oscillating. So if all of the axions, let's say, were exactly the same velocity, even though you have m plus 1/2 mv squared, it will be the case that the signal is coherent forever if all of the axions are exactly the same velocity. So what causes this randomness or this lack of coherence is that the velocity of the axion is not really a constant, right? The axions that are here will have some speed. The ones that are somewhere else will have a somewhat different speed. And the fact that they're different speed basically means that the energy that they have will be somewhat different. And it is that difference in the energy that ultimately causes you to lose coherence.
Okay, thanks.
I had a question about the dark photon search that you mentioned. So the interaction of the dark photon with our standard materials, electrons, is through this epsilon coupling, right? The kinetic mix coupling. So if you have a shield that is strong enough to block all photons, I would assume that you would also block all dark photons because it's exactly the same coupling, and it's the same coupling that would interact with the LC circuit. So why would you have any signal at all?
Good. It's a good question. So basically, it's very important. I mean, I kind of glossed out very quickly that basically in all of these cases, what actually is important. So actually, I can show you my slide and you can see how that works. If you notice, right, in all of these cases, our sensitivity somehow seems to be getting worse and worse at low frequency. And that is precisely because, at low mass. And that is precisely because of the effect that you're talking about. So here is the correct way of thinking about it, which is that I have a shield. And as you said, it's absolutely correct that that when the dark matter goes in, it will drive currents in the shield, and the currents will want to cancel the effects of the photon going outward. But the key point is the following, right? That basically the dark photon, because it has a mass, as so the shields go back and forth, the currents will drive a regular electromagnetic signal outward that will want to cancel the dark matter wave, but the cancellation is not exact precisely because the dark matter has a mass. And the fact that it has a mass actually prevents this exact cancellation from happening. So one way of saying this is that at the shield, instead of the specific basis I talked about, I can talk about the interaction basis, which is the idea that basically, what the shield will set to 0 is this linear combination, a mu plus epsilon a mu. So that one gets blocked. There's a sterile combination that actually goes through. But remember, in this basis, right, is not the mass basis. So the sterile and interacting bases can sort of rotate towards each other because there's a non-zero mass between them. So that's exactly what we're looking at. We're looking at the fact that the sterile component goes through, and the sterile component, once it's inside the shield, will rotate a little bit into the interacting component. And it is that small interaction, that small bit of the interacting component that we actually measure. So in the limit that the mass goes to 0, this rotation doesn't happen. And so the signal goes to 0. And that is basically why in all of our sensitivity plots, you have this slope drying off with that.
Oh.
Hello?
Yeah, not sure what time zone you're in, but we plan to have a discussion session at 2:30 IST, where people
I'm
have
in
follow-up
Japan.
questions.
I think I'll be going out with people here for some stuff.
Okay.
At IPMU. So yeah, if I'm around, I'll join you guys. Otherwise, terribly sorry. But yeah.
Okay, sure. Thanks a lot. Thanks for the nice talk.
Thank you. Bye-bye.